I love this quote at the top from the Holt textbook. Elements vary widely in their properties, but in an orderly way. And we can see that through what we call periodic trends on the periodic table. And that's the great thing about the periodic table is we can use it to make so many predictions about how things are going to react, how things are going to behave. And we do see odd things happen from time to time, but for the most part, elements are changing, but in a common way that we can use and we can predict. And it's just so interesting the way that we finally got a periodic table that helps us see it all so clearly. It's not just a bunch of random facts. So we're dealing with topic 3 again. This is their notes part 2, and we're dealing with some of the physical and chemical properties relating to periodic trends. The main standard that we're addressing here is topic 3.2, understanding number 1. So periodicity, what is it? First, it's reflected as changes within physical properties. It's a trend, which is a predictable change in a particular direction. And the purpose of these trends is to make logical predictions about element behavior. The effective charge, we talked about that in our last notes when we learned that the nuclear charge is equal to the number of protons within the nucleus. And the effective charge then is the charge that valence electrons, we talked about that in our last notes and as well as in topic 2, the valence electrons are the outermost electrons. Those outermost electrons are going to feel a charge from the nucleus, but it's not going to necessarily be the full charge of the protons. And that's because we have energy levels in between. So it is not the same as the nuclear charge once we get to the second energy level and beyond, because the inner electrons feel more of the pull from the nucleus than the outer ones. So those negative electrons are going to interfere with the negatives that are further out, because those negatives are going to repel each other like the same ends of a magnet would repel each other, as opposed to the pulling in that we would normally see from the protons, which are positive, to the electrons that are negative. So the inner electrons are said to shield the outer electrons from the full charge of the nucleus. And we give this a term. We call it the shielding effect. Some textbooks will call it the screening effect. So the electrons that are on the inside shield the outer electrons from the full charge, or the inner electrons screen the electrons on the outside from the full effect. That's going to be a good definition to know, good words to know, good flashcards to make. So we can look here at the effective charge a little bit more, at that shielding effect. We have the nucleus in the middle with our positively charged nucleus. We've got neutrons and protons in there. Neutrons, neutral, not doing any effect on the charge, but those protons are positive and in that dense nucleus, causing H pull from the protons. And then we've got electrons around on the outside. This is the electron of interest, the one that we're dealing with, that is causing a change in the charge, because we've got electrons that are in between, canceling out some of that nuclear charge. And then no electrons on the outside have an effect on the electron of interest because they're out further, so they are not getting in the way of this positive charge. So the trend that we have with this effective charge, and sometimes we can do a Z, which we said was the nuclear charge, with an EFF behind it. So that means that it's no longer just our nuclear charge, it's the effective charge of the nucleus on the electrons that are being shielded by those inner electrons. And we see that as we go from left to right, across the row, we are increasing the effective nuclear charge so that nucleus has a greater effect on the outer electrons. And then as we go from the bottom to the top of a column, we're also increasing the effective nuclear charge because we're getting closer to the nucleus. We have less energy levels in between. So the more energy levels that are between, the lower the effect of the nuclear charge. And because we're getting bigger, we're getting more electrons, and so those more electrons are held less tightly. Those outer electrons are held less tightly, so the effective nuclear charge is less. We also have a trend when it comes to the atomic radii. So first we need to know what atomic radii is. It's the atom size, and it's determined by how far away the electrons are from the nucleus. And we know those electrons are constantly moving around, but it's the electron energy density. So where are we most likely to see the electron from the nucleus? And so we often have to take two nuclei and have them bonded together like Cl2, and then we would find the distance between those two nuclei and divide that by 2. So that's one of the common ways that we determine the atomic radii. There are other ways to determine it as well, depending on the types of bonds that are involved. Metallic bonds and ionic bonds, we can use different types of bonding to determine what the radii is. If we're just looking at one atom, we can't pinpoint where any electron is at any given time, and so that makes it very difficult for us to look at just one individual atom that's not bonded to anything else and determine its radius. So as we go from left to right on the periodic table, the atomic radius actually becomes smaller. And that's because the nuclear charge is increasing because we're adding protons to the nucleus. And the electrons are all being added to the same energy level. So since we're adding more protons and more electrons, those positive and negative charges are going to be pulling each other in more. So the effective nuclear charge increases, which it pulls the electrons closer to the nucleus because it's like those magnets of opposite poles. They're pulling each other towards the nucleus even more. So it's getting smaller, even though I'm adding more protons and electrons. As we go from the top of the periodic table to the bottom of the periodic table, so we're looking at a column now, let's say it's lithium to francium, we're going to become bigger. And that's because we're adding another energy level from one period to the next. The inner electrons are going to shield those outer electrons. We're getting back to that shielding effect. And so it becomes bigger the further down we go. Here's just a nice little image of what that atomic radii trend is. We go smaller as we go left to right, and we get bigger as we go top to bottom. Some examples. So which of the elements in the pairs would have the larger atomic radii? I look at my periodic table and I find bromine and chlorine, and I see that bromine is lower than chlorine, and they're in the same column. So that must mean that it is going to be larger than the chlorine. And then we have zirconium and niobium. Both of those are transition metals. I find them on the periodic table, and it's atomic number 40 and 41. I see that zirconium is to the left of niobium, and so it is the larger one because I know as I go across from left to right, it becomes smaller. So the zirconium must have a larger atomic radii. Here's some exceptions. The noble gases are an exception to this general periodic table rule because it has a full outer energy level. There's little interaction between electrons, and so we can't use our current tools to make the measurements that we normally would. Those electrons are moving so fast and we can't determine where exactly they're going to be, so I can't just take a ruler and say, here's my nucleus, here's my electron, what is it? Because there's no way to actually bond it to anything else for the most part. Ions also have radii. So as an electron leaves or comes into a nucleus, that's going to change the radius of that previous atom. So the radius of an anion, which we know is negative because it's gained an electron, a negative ion, anion, or a cation. I positively love cats. That positively charged ion, which is because it lost an electron, are going to be compared to their parent atom, so what they were to start with. Positive ions, the cations, which we know are our metals on the periodic table, are smaller than their parent atoms. That's because they've lost their outermost electron. Negative anions, on the other hand, the anions that are from nonmetals, are larger than their parent atom because they've gained an extra electron. There's more opposite charge, so it's going to get bigger than it was to start with. So lithium would have an electron configuration of 1s2, 2s1. The electron configuration for the lithium ion after that metal has lost its one valence electron would be 1s2. So we can see that there's no more electrons in the second energy level, so the radius of this cation is smaller than it was as an atom. So Li1 plus is smaller than Li. Here's an isoelectronic series, which means all of these have the same electron configuration after they've become their current ions. So they are all a 1s2, 2s2, 2p6. Up here we have what they were before we formed ions. So oxygen as an atom would be 1s2, 2s2, 2p4. But here we've gained 2 electrons to become O2 negative, and now it's an 1s2, 2s2, 2p6. We can see that the oxygen and the fluorine are bigger than neon, which has the same electron configuration, but they have more protons, so there's going to be more repulsion than there was to start with. The sodium and the magnesium have both lost electrons but have the same number of protons that they did originally, so they're going to pull in those electrons even more, making it even smaller. Isoelectronic series would be a good definition to make on a flashcard. It just means that they all have the same electron configuration, even though they have a different number of protons and they all have different charges. We can see that the ionic radius is increasing as we go from the middle of the periodic table over to the alkali metals. And as I go from that middle, that fourth group where carbon is, over to the halogens, I can see that my ionic radius decreases. So this would be another good trend to memorize. Okay, the ionization energy is the energy required to remove an electron from an atom. This is an endothermic process. It requires energy, so the values of these ionization energies are all positive. An atom we know is neutral, and to become a positive ion, aka lose an electron, there must be some energy put in. That's where we get that endothermic process. The energy that's required to remove that electron from a given element is a constant for that element. It is a unique property. We often call that a characteristic property. And for our ionization energy, as we move left to right on the periodic table, we become bigger. It takes more energy. So as we go to the right, we need more energy to remove or take out an electron. And that's kind of what we've been seeing. We know that halogens are so close to being noble gases in the same isoelectronic series. It'd be much easier for them to gain one electron than to start removing them. So it takes a lot of energy to remove one because they would much rather gain one. As we go to the right, atoms want to gain electrons, not lose them. As we go from top to bottom, our trend becomes smaller because there is less energy required to remove an electron as we go down the column. And again, that's due to that shielding effect. The inner electrons block the attraction of the protons to the outer electrons. They're not held as tightly, and therefore it doesn't take as much energy to remove them. Here's our trend summary. We have a bigger ionization as we go left to right, and it's smaller as we go top to bottom. This is opposite, notice, of the atomic radii trend. So, which would have the larger ionization energy? Which would take more energy to remove an electron from? We're looking at the same elements that we had before, bromine to chlorine. We see that they're both halogens. They're in the same column. Chlorine is above the bromine, and so it would take more energy to remove an electron from the chlorine than it would from the bromine. And again, zirconium and niobium, atomic number 40 and 41. It would be easier to remove an electron from the larger zirconium than it would from the niobium, which means the niobium has a larger ionization energy. It takes more energy to remove an electron from it. Electronegativity is a different term to make another flashcard for. It's how strongly an atom attracts electrons of other atoms to itself. So you can see this unit requires a lot of reasoning, but also a lot of definition memorizing. So flashcards are going to come in handy. This is closely related to the ionization energy, but they are different things. Notice our definitions are different, so make sure you know that they are different, but the trends are the same. As I go from left to right, the electronegativity increases. As I go top to bottom, the electronegativity decreases. We also have a trend for the electron affinity, and we do a big E because it's relating to energy, and then we have a lowercase subscripted EA for the electron affinity. So it's the energy of the electron affinity. And there's two ways we could define it. We could define it as the energy required to detach an electron from an anion in the gas phase, which would be, we have an anion here, and then we've got our atom plus an electron that's detaching the anion from it in the gas phase. Or the other way we can determine or define it is the energy released when 1 mole of electrons are attached to 1 mole of atoms. And so here's my atom of whatever my atom is, no charge, and then we have an electron here that gets attached to my electron or my atom becoming an anion. It's an exothermic process, so the energy value is going to be negative, so all of my electron affinity values are going to be negative. The more negative the value, the greater the ion attracts to the electron. The trend for it, there is more variability in this trend than the other trends, but in general, as we go left to right, we're becoming more negative. As we go from top to bottom, we're becoming less negative. There are some positive energy of electron affinity values, meaning that they are unstable as an anion. So whenever you see a positive EA value, that means that it's going to be unstable as an anion. Here's a little visual summary for you, taken off the internet. The picture is in your notes along with the citation for it. The only thing that we didn't talk about is the metallic and non-metallic characters, and we're going to be talking more about that in our notes in part 3. The non-metallic is increasing as we go from bottom to top and left to right, and the metallic character increases as we go top to bottom, right to left. In the new syllabus, you do not need to know about melting point trends. At this point in the year, at least, the old syllabus, if you're looking at old books, it talks about melting point, so do not pay attention to the melting point part of the reading. It's not going to be necessary for you. It is, however, very interesting looking at the trends of the alkali metals and the halogens. The halogens alone, you can look at the periodic table in our classroom and see what the trend is, because we know that the reds on our periodic table in the classroom signify a gas at room temperature, the blue a liquid at room temperature, and the black solid at room temperature, and those are all within that halogen group.